G'day. I was trying to do some measurements recently of low resistances and a few question marks appeared, so I was going to use this meter down here, and then because of these question marks I pulled out this one and this one to do some corroboration and brought this one out for completeness. That one's busted, but so there's my Hewlett-Packard 3450 series multimeters or voltmeters. They don't do current. They do AC volts, DC volts and ohms. And yeah, I just thought I'd do a bit of a rave and a few measurements and finally get around to showing you the low resistance measurement I was trying to make. What we've got here is two 3456As and two 3455As. So they're a bit older. I think these are about 1980, 1981, and these are about 1976. And they're big brutes. Look at the depth of them. They go back for several kilometres, so they take up a lot of bench space. And I think I got this one first, then I think that one, then this one, then that one. I bought these three on eBay. I think the prices were in Australian dollars, $3.50, $2.50, $1.50 and $20 because that one was busted. In fact, these two came from the same guy. I bought that on eBay, and then at a swap meet he had this one, and he told me that on the morning of the swap meet he turned it on and smoke came out the side of it, and that's why it was only 20 bucks. So, and I've done a video on this where I just opened it up and had a quick look inside to see if I could spot the cause of the smoke, and nothing obviously burnt, so that one's got promise. The power supply voltages all looked good, but if we turn it on it'll see it's got a noisy fan. Both these have loud fans. These ones are fanless. If we do the test, it gets error 11 and 10 and 9 and 8, not 7, 6, 5, not 4, 3, 2, 1, 0, and then there's the lamp test. So yeah, that one's got issues, but these other three are all good. No fans on these guys, and this one's got a fan. This one, whenever I turn it on, the fan blows out some sort of a smell that reminds me of old ladies' underpants. Not that I have any experience with that, that's just my impression. But it always hits me every time I turn it on, there's this smell comes out of it. Obviously they've gone to a smaller display on the later model. Also, this one, the display is much brighter. Much brighter than this one. Not sure why, if this one's faded or if they use different, are they different colours? I'm colourblind. Are they just different brightnesses or are they actually different colours? Not sure. These two have a crystal inside them which you change depending on whether you're running a 50 Hz or 60 Hz mains power supply, and they're very odd crystals. They're not a standard value frequency at all. And this one had, we're 50 Hz here, this one had the 60 Hz crystal in it, this one had the 50 Hz, and I got this from a guy in Tassie, and he also had a spare crystal, 50 Hz crystal, which he sold me also for a good price. It's just $7 delivered, which is here. I haven't put it in yet, but that's a 50 Hz crystal for this bottom meter. It has to do with the number of power line cycles that it averages the readings over, and I don't know why they have to use a crystal like that. Surely they could use the actual incoming power line to detect the frequency and derive several megahertz that those crystals operate at from the power line, but they didn't. So that takes the total cost of these plus the $7 for that to $777. Isn't that cute? Let's just give them something to do. We've got here a lithium-ion battery pack. Very nice unit. It's about 16 volts, and I'll set it up so that these 3 meters are measuring the voltage coming out of that. So there they are, all measuring this voltage, and look how close they are. Now these three, well, this one was certainly made at a different time than these two, and possibly in a different place. These might have even been made in a different place and different times. That was 45 years ago when these things were made, and they might have been together at one time, but they've been apart for all that intervening time, lived completely different lives, and now they've been brought back together, or together for the first time, and look how much they agree. And this one looks like it was calibrated in 2001. These are unknown, but yeah, the agreement's just remarkable, and we can increase the resolution on them. So now they're disagreeing by what? 0.2 of a millivolt, 200 microvolts. These two, and this one's about 3 or 4 tenths. So that just amazes me how close they are. And just for fun, let's throw in a couple of other cheapo meters. Here's one of those little Anangs that are quite popular. And to the limit of his resolution, he's pretty much right. Should probably be, yeah, that is correct. No, should be 16.65 if you round those up. This $7 cheapie, try not to short these things, it will be big sparks, because these things, each cell can deliver 80 amps, and there's 2 in parallel, and then 5 lots of that in series. So even this cheap ass one's pretty good for a $7 meter. I have noticed over time, these have been warmed up for a while. I've just powered on one again, but they've been on for a while, so they're fairly warmed up. And the voltage is gradually dropping out of this, I think, because that's recently charged. I think the batteries, when they first got a load, they drop a few percent fairly rapidly, and then they plateau until they hit the end of their capacity and then die in the arse. But so this could be, with 10 megohm impedance on each of these meters, so that's 50 megohm load. It's putting a very slight drain on the battery, so it might be just coming down that first few percent before it hits the plateau. So that's why the voltage is dropping over time. Yeah, so isn't that good? The other day, I was trying to do a measurement, as I said, of this low value resistor I've made, and I was getting unclear measurements. That's why I brought out the second one, and then I thought I'll get this one out as well. And I turned him on. He hadn't been on for a while, and he went for about 5 seconds and then just shut down. No, sorry, no, I put them all in test mode first, so got to disconnect these for that. Disconnect the battery first so I don't short any leads. I had that in the wrong socket. Luckily the guard was in, so they're connected together. Yeah, put them in test mode. This top one is test fails, but the others go through the display, do some tests. If they all pass, it shows the display lit up. So it's all working. But this one, I did that, and then press test to turn it off. But it doesn't turn it off. With these guys, you just press test and it comes out of test mode. These ones, I didn't realise till I read the manual later, you have to press one of these buttons. And I pressed all these other buttons trying to turn it off, and it wouldn't come out of test mode. So I turned off the power and then turned it back on, and it ran for about 5 seconds and then shut down. And tried again. 10 seconds, 15, I could get maybe 20 seconds before it shut down, which really bugged me, because to fix this one it would be really nice to have a working one to compare against. And in fact the service manual suggests having a second one, because there's a cable that connects the in guard to the out guard section. You disconnect that on both, and then with a special service cable, which I imagine wouldn't be too hard to make up, my own one, you join the in guard of one to the out guard of the other and see if the problem shifts. So you can isolate it to either in guard or out guard section, and of course you would have made sure the power supplies were good, and yeah, that would have been a big help. And if this thing was broken, so I called it a day on those, and consulted the schematics for this guy, and there's nothing that can turn the power off under some fault condition. no relay or whatever. The only thing that turns off the power is this switch. So that had me scratching my head. And so the next day I turned it on again, and it worked. Didn't shut down. So I turned it off, but it didn't turn off. In fact, I unplugged the power cord at the back. So luckily, it's just this switch, just a dicky switch. It hasn't played up today, but yeah, just a bad switch, which should be pretty easy to fix, I imagine, unless it's a strange one, because there is a push rod thing off the back of it, I believe. So who knows what the actual switch looks like. So I'll have a good meter to test this guy, and the feelings are stirring in the back of my mind to actually get together and work on these 2 meters, get this one going, check out power supply capacitors and everything in both of them. So that's the introduction to all these meters. Let's turn that guy off. I'll just check those volts again, see how it's going. So there's all the meters connected again and showing there very good agreement. These two are exactly together now. Let's increase the resolution. Yeah. So still the 0.2 of a millivolt difference there, only 1 or 2 there. And this one's still, you should be rounding it up to, should be 16.65. It is sometimes, so it's very close. This one's a little bit high, but $7. So now I'll try measuring the resistor that I was originally started all this with. And so I wanted to measure some currents recently, AC, up to maybe 20 amps. I got a bunch of various shunts, but current shunts for measuring resistance, but here's a brute. This one's 300 amps. I don't know if you can see it there, 300 amps, 60 millivolts. And this one's 100 amps, 100 millivolts, so 1 milliohm resistance. And I wanted to get a slightly higher shunt resistance, maybe 10 milliohms, so that the developed voltage was clearly in the range of the meters, so that there was no errors due to it being so low that almost couldn't measure it. So I decided to make my own current shunt resistor, which is this guy, and that's actually 22 resistors in parallel, and each resistor is 0.22 ohms, so that makes a 0.01 ohm resistor. Now this was an attempt to heat sink them so that they wouldn't get very warm, so their temperature coefficient wouldn't change their resistance too much. They're only making loose contact. I had an idea of using heat sink compound in there, but that turned into a bloody mess. But I think I've got a way of fixing it, but I won't try that just yet. So that's what I wanted to measure. So if we use this guy, switch it to ohms range, and then measure the resistance, we get 0.15 ohms. Yeah, you can stop your screaming. I know that's not how you measure low value resistances. I'm just seeing if you're paying attention. Yes, to measure resistances that low, you have to use a 4-wire Kelvin connection. And if you don't know what that is, I'll just briefly explain it. A digital meter measures resistance by passing a known current through the unknown resistance and then measuring the voltage that develops across it. And then it can calculate the resistance using Ohm's law. The unknown resistance is equal to the measured voltage divided by the known current. Trouble is, it can only measure the voltage over here at the terminals. It can't measure it there, which is where we really want to measure it. It can only measure it here. So the resistance it comes up with includes the resistance of the leads. Now for a resistance of several ohms, say 10 or more, that's not an issue. The resistance of the leads is much less than 10 ohms. But when you're trying to measure below an ohm, the value of these really throws the measurements out. So the way to fix that is with Kelvin connection and 4 wires on. That's using leads like this with 4 wires, and each wire goes to only one of the prongs. They only connect when they touch like that. like this. Those two black wires, there's no connection between them, only when you let it close. So what you do is plug. So in 4-wire mode, which we switch here, these two wires, one on each lead, they send the known current through the resistance, through the unknown resistance, and the other two measure the voltage, and they're measuring it at the resistance there, because there's no current running through them, so there's no voltage drop across the leads, so it's measuring the voltage here. There is a voltage drop across these leads, but that doesn't matter because we're bypassing them for the measurement. So now we get a much lower reading, 0.01 ohms. Now this should be, that's not bad, but it's a bit high. I would have expected to be much closer to 0.01, like 0.0101 maybe. So I'm a bit unsure about my measurements in it. I did a lot of mucking around. If I measured different parts of this, it would give, I think there gave a better value. No, it wasn't there. But you see, it's considerably different, just measuring a different point on these connections. Now that might be dissimilar metal thermal effects, I'm not sure. But that's why I brought out the other meter. So let's see what he says in 4 ohms mode, 4-wire mode. Switching to this meter, similar sort of issue. It's not 0.01 and a very little bit. So we'll try this guy, 4-wire. Now that's better. So this meter doesn't show ohms, it only shows kiloohms. So that's 100 ohms, 10 ohms, 1 ohm, 10th of an ohm, 100th of an ohm. So it's very close to 0.01, but it's actually less than. That shouldn't be happening, because all these resistors, I measured them all individually, and they're all slightly higher than 0.22 ohms. So I can't see how it could be ever less than 0.01 when you include other resistances as well. It can't possibly be less than 0.01. Yeah, disagreement. So to try and sort that out, I made another resistor, this guy, which is 34 680 ohm resistors in parallel. So that should be 20 ohms. Yeah, so I want to use that battery I had before, put this and this in series with that battery, measure the voltage across the battery, across here and across this guy, and hopefully, because we know that the 3 meters are very agreeable on voltages, get a more definitive value for the resistance of this. So I'll set that up. So this mess of wires should be such that the battery goes into this 20 ohm resistor. I should have measured that, I'll measure it in a minute. But it is very close to 20 ohms, 19.98 I think it was. Through that resistor, hoping lead resistances won't be an issue here, through that resistor and back to the battery. And the top meter is measuring the voltage across both resistors from the battery. This one's measuring the resistance across the 20 ohm resistor and this voltage, and this one's measuring the voltage across the 0.01 ohm resistor, and we'll see if the numbers add up. Now I think there's going to be about 20 milliamps, sorry 800 milliamps flowing through here, and that will make these resistors run at about 300 milliwatts, so a bit over half of their rating. So they will get warm and their temperature coefficient may change the reading. So if that's why I've got the 3 meters connected at once, so we can run the video and at any time we can just pause and check the readings. So let's see what happens when I connect the battery. Hopefully no sparks. So we have some numbers. 16.45 coming out of the battery, 16.38 across the 20 ohms, 9.5 millivolts across the 0.01 ohms. I don't want to run it for long. Well, let's run it for a little while and just see if the numbers change very much. See if there's any warmth coming out of these guys. Yeah, they're getting quite hot actually. So enough of that, we'll disconnect it. Maybe I need a heatsink arrangement like this for that guy as well. Or more resistors. I got 1,000 of them. I could come up with parallel and series combinations to get the same resistance with a far higher wattage rating, but let's just stick with 34 for now. Now I'll stop it and review the voltages we measured. Oh, I'll measure the resistance of this guy while we're here. The idea of doing that was the resistance of this can be measured, I believe, with more certainty than the resistance of this. So, and then using voltages, which we know this thing agrees on, these things all agree on pretty well, hopefully get a more accurate reading for this. Back to 4-wire mode. Don't really need it for 20 ohms, but, well, yeah, probably do actually. I'll use a middle meter. 4-wire, they're still a touch warm, not very, they've cooled down. 19.985. 19.985 I'm going to call it. I'll go up and do some calculations. Okay, I've done my calculations and produced a little document for future reference. The issue is I've got these two resistances. This one's nominally 20 ohms, this one's nominally 0.01 of an ohm. Now I can measure that with a fair degree of certainty at 19.985 ohms, but this one I'm uncertain. So the aim of this exercise is to come up with a better value for this resistor. Now my method is to use a circuit like this, put them all in series with a battery and measure the voltages across the two resistors. And because I'm pretty happy with knowing the value of this resistor, the voltage across it tells me the current through both. And then measuring the voltage across this with that same current, I can calculate the resistance of this. The theory behind this is that the HP345x, when it's measuring below 100 ohms, the current it's using, the test current, is 1 milliamp. So for a low resistance like this, the voltage that it's measuring is down in the microvolts, and things like thermoelectric effects caused by dissimilar metals can account for a few microvolts, so it can throw the readings way off. Maybe this is a naive way of doing it. I don't really think so though. Maybe I should be using a Wheatstone bridge, but for that I think I would also need a resistance similar to this with an accurately known value, so that just puts me back where I started. So I'm going to use this method, and the theory is that by running it at a much higher current, 800 milliamps instead of 1, the voltage across this is up into the millivolts rather than microvolts. So the thermoelectric effects and contact resistances and anything else that can throw it out are reduced. They're down in the noise floor and we're risen well above it. Also, it bypasses any issues in the multimeter that might be there with the calibration in the ohms range or the reliability. Maybe they're just not very good when you go down this level. I'm not sure. And we're bypassing the ohms current generator, some switching and stuff, just using it as a voltmeter, and we know that these 3 voltmeters are pretty accurate because they all agree when we measure the battery voltage. But if there's any ohms nuts or volts nuts that have any positive comments on that, I'd be interested to hear it. But I think this is valid. So there's our test setup. Because this thing gets pretty hot, almost too hot to touch, which I figure is like 60 degrees Celsius, it did that within maybe half a minute. So the test only ran for half a minute, but from the video I can see the voltages when I first connected the battery and just before I disconnected it when it was hot. So I've got these 2 measurements, cold and hot, for both resistors. Here's my calculations. For the cold situation, when I first turned on the power, we got those 2 voltages. So the circuit current running through both of them is the voltage measured across here divided by its known resistance of 19.985 ohms, which gives this current. Then dividing the voltage measured across this by that same current, because it's running through both of them, gives us this value for resistance. And rounded up to 3 significant digits, we get 0.0117 ohms. Doing it again at the voltages measured when it was hot, we get a slightly lower current and we get a slightly lower resistance value, but it still rounds up to the same thing. Now the issue there was, of course, that when it was hot, was this still 19.985 ohms? It may have changed. So to investigate that, if we look at what each individual resistor here is, so we divide that, multiply that by 34, we get 679.5 ohms. which makes sense because I measured a bunch of these resistors and none of them were as high as 680 ohms. They're all a little bit less. And the ones I used in this all had a 679 handle. So it's completely unsurprising that the average of them is right in the middle of the 679 range. And they are Vishay MRS 25 resistors. There's the specs. And the datasheet also gives a maximum resistance change at full power dissipation. Now we're maybe at 2/3 of dissipation, and not for 1,000 hours, only for 30 seconds. But there's the formula it gives for it. And so that's the worst case. So we apply that to this resistance for each individual resistor, we get a possible change of plus or minus 3 point something ohms. Now, assuming it's a positive temperature coefficient and that it's added to the resistance, that value for each resistor plus this much gives that value when it's hot. And then 34 in parallel makes the combined result 20.086. If we then recalculate this resistance for this using this value for resistance instead of the 19.985, we get this current, and it leads us to this resistance for him, which when rounded gives the same as we got before. And that's worst case resistance change. Now if it was subtracting rather than adding this small amount, this small resistance change, I've done the calculation again and we get a slightly, ever so slightly lower value of resistance, but I think it's more likely that it went up because the resistance dropped. Sorry, the current dropped, so I'm assuming that that's because the resistance went up slightly. So yeah, that is my now definitive value for the resistance of this thing. And just for fun, because we also measured the voltage across both resistors from here to here, effectively the battery voltage, but measured at the resistors, the difference should be accounted for mostly by this clip lead that I used to join them and contact resistances, etc. So there's some missing volts. If we take that voltage measured across both resistors, subtract the two voltages measured across each individual resistor, we get this missing voltage. And for the cold current, that gives a resistance for this stuff, or the whole, whatever's missing, maybe it's in the other wires as well, going to the battery, but we get this value for resistance, and at the hot, slightly higher. And that's about 5 or 6 times more than the resistance of this. I don't know what that means, probably meaningless, but just for fun, we have that as well. So, I now have a value I can use for calculations involving this thing, I hope. 0.0117 ohms. And I want to do some measurements of AC current using at mains voltage for some those little energy meter things you can get. I've got a few of those, but the currents they show are all over the place. So I want to use this to get a definitive value for current, measuring the RMS AC voltage across it, and then I'll know the current in the circuit and see what those meters say, trying to work out which ones are the most accurate. That was the aim of this exercise. So I hope you found that interesting, and if you did, please give it a like, and I'll catch you later.